Thank you, Mark. Everybody again. My work tries to answer this question that do cells perceive diffusion noise? And it's interesting. I just if the answer is yes or no, how many people here think can answer positively to this question?
Do I get the vote?
Yeah.
But my name's on the paper.
Raise hand. Yeah.
Yes.
Yes. Just one person. Okay, then let's see what happens. And I try to give an answer to this question. This work is a joint work with people in AstraZeneca, Sweden, David Jönsson, Peter Janneberg, and other nobles here. Let's start with a very briefly introducing Brownian motion and diffusion. It's very clear for all of us somehow. But Brownian motion is the random walk of small particles in a fluid. It's discovered in 1827 by Robert Brown. In a microscale perspective, this is related to the individual particles. Each particle is moving randomly in any direction. This is the Brownian motion from in a microscale perspective. But if we look at the collective behavior of the molecules, this Brownian motion of individual molecules collectively leads to a microscopic property which we call diffusion, and means that molecules from a region with higher concentration move towards a region with lower concentration, and this is diffusion. Now let's have a look at the diffusion in living creatures, cells, or body, and in living organisms. We know that diffusion has an important role because the cells, as the building blocks of the organisms, if we can consider the level as the building blocks, the cells are communicating with each other based on diffusion. Almost all cells have kinds of devices or equipment to communicate based on diffusion. Also, cells need to sense their environment to get their food and nutrition, and also as part of communication they need to sense the environment. In this process of sensing the environment, which is related to the diffusion process, we have different noise sources, which are known, and biologists, experimental biologists look at that, particularly people that work from a computational point of view. Two noise sources are intracellular noise, which, if you look at this, is the membrane of the cell. It's part of schematic representation for a cell, part of a cell. And this is the environment, extracellular environment here. And this is, for example, signaling molecule, the receptor. And a signaling pathway is required for cell to understand this, the existence of this signaling molecule. And this intracellular noise is related to this signaling pathway here. And this means that if you apply the same stimulus to the same cell, but you may receive different response. This is intracellular noise because there is some noise here. While we may not be, these kinds of noise part of them can also be diffusion and chemical reactions that are happening here. The second important noise source is cell-to-cell variability, and this means that different cells of the same type may respond differently to the same stimulus. This is because of the cells, even when they are from the same type, they have different, they may lead to different responses. And this is called cell-to-cell variability. But let's talk about diffusion noise, which, based on my exploration, the experimental biologists ignore this kind of noise, interestingly, because maybe they think that the other noise sources are more important. But let's discuss about the diffusion noise and how it may have an impact. If I just back to the previous slide, this is the input when you apply some concentration of molecules to a cell, and this is your input. And my question is that how this input signal and variability in this input signal, which comes from diffusion, may has, a kinds of impact on the response of the cell, which is ignored in the works that we see from biologists and particularly people in computational biology. In molecular communication community, we have worked on this problem for now, we can say, a long time. We have theoretically modeled receivers. Sometimes we consider transparent receiver, where the simplest type of receiver that we look at. There is nothing, and we just assume a transparent receiver that, okay, the molecules are coming there, and then we can count them. This is kinds of modeling. But the missing point is that the practical constraints on the sensitivity or computational capacity of the receiver is ignored sometimes. Also, we have also works that are considering the effect of receptors over the cells, but fundamentally they don't consider the effect of sensitivity of the cell and the need of the cell to sense something. It's somehow related to the Morizano talk because it was related to the meaning of the information for the cell, and I can connect this with previous talk. And this problem has been considered also in physics community. There are some papers that they provide for fundamental physics limits for chemical sensing of the cells, because it's an important problem for them as well. But my question here is a related question but different, and it's given a certain level of cell sensitivity to measure concentration, how much uncertainty observed by the cell is due to the diffusion, Brownian motion. Right? Then what I want to consider is giving a certain level of sensitivity to the cell and fundamentally explore, given this assumption, how much the signal that the cell receives is noisy based on that sensitivity of that cell. The system model is something like that. Assume that you have a cell of volume VC, for example. Assume it's in a liquid with signaling molecules, of a fixed concentration. X is the concentration of the molecules around. It's fixed. And a very simple system model. Now I want to define the cell sensitivity. This is something that is missing in previous works, and it's defined as accuracy of distinguishing different number of molecules. I call it delta, means that it's like the cell can just quantize the number of the cells in a level delta, something like this we can assume. And I also define the sensing region for a cell, which here is the same order of the size of the cell. Then usually the cells can sense certain distance from them. It can be in the order of the cell size. And this is the sensing region definition. The number of molecules in the sensing region, which is that we see, then would be, it's easy to show that it would be a Poisson random variable, which is concentration times the volume of the sensing region, and n0 is the Avogadro number if x is in terms of molar. Then the number of the molecules would be such random variable that we have. And the quantized version of n by the step delta, I define as n delta, this is the thing that cell is measuring. Then the cell doesn't receive this signal. For a cell it's not important to count exactly the number of the molecules, but maybe an accuracy of the level delta that we don't know exactly, but I will say that we can estimate that. Then this is the thing that the cell is observing. And if this delta is, for example, for here, if it's 4, then it's kind of threshold understanding of the signal for the cell, right? Then this delta can show the sensitivity of the cell, even the binary case. Okay, now I want to propose measure this uncertainty of the cell. I call this normalized entropy measure. Simply, it's just ignore the denominator here. It's entropy of that random variable that I introduced here, this n delta, which is the cell's observation. Okay. Then this is entropy, but entropy of quantized version of the number of molecules. And just I divided by the maximum entropy of the discrete random variable over n1 to n2 is assume that the cell just responds to a range of signaling molecule concentration. It should be something between n1 to n2, different for different cells. Then for step delta, this is the maximum thing that you can have. Then it's a normalized measure between 0 and 1. Then this measure considers accuracy of the cell. It's normalized between 0 and 1, then enables comparing different cell types and different molecules. And it's going to be a general universal measure that we can use in the future. And just to give a sense of this measure, I have considered glucose as a very high concentration molecule in our blood, and hepatocyte cells in the liver as the receiver of this glucose. And also, the dynamic range is from 2.8 to 11 millimolar for glucose in blood. And this is the N1 and N2. And also I have considered a very low concentrated molecule in the blood with parathyroid hormone and also the kidney cells as the receiver of that. And I have they have plotted the measure, the normalized entropy given the cell sensitivity delta. Delta, smaller delta means that cell is high sensitive because it can measure lower, and for higher delta you have low sensitivity. As you see, this is not a strictly increasing and decreasing function, and also, for example, for the hepatocyte cells, you see even by steps 1% also still it's zero. The cell doesn't sense any noise because the entropy is zero here, right? And when your cell is low sensitive, then you don't have any noise, right? Even for very low concentrated cells, you see that if, for example, for 0.1 times the dynamic range, if the delta is in this range, still you don't see, the cell doesn't feel any noise of diffusion. Thank you.
Thank you very much. Maybe we can take one question only, a very quick question in the audience. Yes, please.
In the initial model that you laid out, are you looking at individual cells or are you looking at cluster of cells?
Yeah, here I just consider a very fundamentally system model that was just one single cell. Yeah. The VC that I mentioned was just the volume of one cell.
And in place going forward is how do you imagine a cluster of cells would respond to necessities?
Yeah, that's a very interesting question because always we see the cells in the populations, not individually. But any cell has a sensing region, and then we can think about the understanding of individual cells of the environment. But when they come in the populations, then sometimes the response is the collective response of them, which this collective response is averaging of the individual cells, which leads to a lower noise level in your system because you are taking an average of many. Yeah. It's like observing too many observations and averaging more than them. It decreases your noise level.
Thank you very much. I guess we will not be able to take another question, but I have some questions, but I will ask them over the dinner.
Yeah.
Okay, thank you very much for this.
Yeah.